Okay, hello, Dr. Dolman. So, for some context, when we were in chapter 9 or chapter 10, whichever one was about our stinking citric acid cycle and electron transport chain, whenever we were talking about cyanide and how that kind of blocks off the electron transport chain and how it doesn't allow completion, I thought that was like the most interesting thing ever. I'd always known cyanide was harmful, but I never understood why. So, in this presentation, I decided to look at some of the other chemical inhibitors of the electron transport chain, just because I thought it was interesting. So, we're going to talk about cyanide again, but we'll talk about some other neat stuff. Oh gosh. Okay, so just as a quick refresher for everybody, how does the electron transport chain work? Let me get my little pointer. I don't have a pointer. You can annotate. Oh gosh, it's not letting me do anything. Whatever, okay. So, we donate 2 electrons through NADH. We use the energy from each electron moving through each of these complexes. We've got 4 complexes, however, we're really only concerned about complex 1, 3, and 4, at least for our purposes right now. With the release of energy as the electrons transfer from complex to complex, that allows hydrogen to move up its concentration gradient into the intermembrane space. This will happen each time an electron flows through a complex. Here we create our proton gradient, which is used by ATP synthase to actually make ATP. So this is an oversimplification of the process, but it's important that we just understand we have NADH, it'll donate electrons, this electron travels from complex to complex. At the end, it'll meet with oxygen, which is our final electron acceptor, and will produce H2O, and then ATP synthase will do its thing, and we will get 3 ATP, or rather 1 ATP for every 3 hydrogen. Okay, so let's talk about cyanide. So we spoke about this in class, but we've got our target. Our target is the iron copper center of cytochrome C oxidase. So this is over here. I hope you can see my mouse. Over here on complex 4. We've actually got 2 iron copper complexes. However, one is Fe2 plus, one is Fe3 plus, and that does matter, and we'll get to that in a second. So cyanide, this highly electronegative molecule, will bind to iron, this very positive molecule. So when we bind to iron, electrons cannot make it to oxygen. So if we look back at this picture all the way back where NADH starts, we drop off 2 electrons. And if we just follow this red arrow, it'll come all the way around, all the way, until here. And over here in complex 4, where we have these iron copper complexes, it'll make its way past into oxygen. But think about it. If we have this cyanide, and it'll bind to that iron and that copper, it effectively does not allow the electrons to go any further. They want to make their way through, but now we've got cyanide in the way. Boom. Complex 4 is stopped. So the effect, electron flow cannot continue. The electron gets stuck right there, can't go any further. Proton pumping ceases. So now if electrons aren't moving through, they're not releasing energy, the protons don't have the active energy to go up their concentration gradient. And if that proton pump ceases, ATP production will collapse. We no longer have that gradient, which is our power for ATP synthase to occur. So the outcome, the cells will compensate and attempt to switch to anaerobic metabolism. In this sense, they are switching to like glycolysis. But we've talked about this. When glycolysis doesn't have oxygen, we produce lactate. And here we get lactate acidosis, or an excessive buildup of lactic acid in blood. in my previous teach me's, I talked about how this is okay in exercise because it's so acute, it's so short term. The muscle environment will get acidic, and then our set stops, and then we breathe, and we return to normal. But here, we can't get oxygen through how we need it to. So the lactate will continue to build up, and eventually this leads to cellular hypoxia, or a state where cells can no longer use oxygen effectively. And this will kill you, and it will kill you relatively quickly. So cyanide poisoning is acutely lethal. It's quick, and you will probably die. So I've always understood that carbon monoxide is dangerous. However, I've never understood why. So carbon monoxide is dangerous on two fronts. There's one that's less relevant to us in the context of this class, which is just hemoglobin binding. We will find out that carbon monoxide wants to bind to iron. Think about that. It wants to bind to iron, specifically the iron in hemoglobin. Therefore, oxygen can't be transported any longer. If our red blood cells, with their hemoglobin, if they are binded to by carbon monoxide, that means oxygen can no longer also bind to them. And they actually will outcompete the oxygen. So now we've got these red blood cells with carbon monoxide. Well, that doesn't do us any good. So it's kind of weird. The blood will remain oxygenated. It looks like the blood has got oxygen. It looks good, but the actual tissues are suffocating. They're not actually getting any blood. So it's dangerous on that front. But if we think to electron transport chain, we see a similar effect as in cyanide. Similarly to cyanide, the carbon monoxide bonds to an iron. So remember, if we go back one slide, we've got two separate iron-copper complexes. Well, I mentioned that one of them was an Fe3+. That's the one where cyanide will typically bond to. However, carbon monoxide bonds to the Fe2+. And then the same kind of chain of events happen. Electron transport is halted, the proton pumps are halted, ATP production is halted, and we will lead to hypoxia, and so on. Another thing that's kind of interesting, though, if you know about pulse oxes, we use these in the hospital. We put this on, and it'll measure the degree of saturation of oxygen for blood. The numbers will still appear normal even if someone has carbon monoxide poisoning, because all the pulse ox is reading is if the red blood cells have something bonded to them, essentially. And in this case, they do. It's just not necessarily oxygen. So I found this quote from a specific source that talks all about carbon monoxide and cyanide and some of the other ones we're going to talk about in a little bit. But when carbon monoxide is bound rather than O2, a patient's pulse ox may still appear normal and cannot be used reliably. I thought that was super interesting. I'd never considered that, but just a little clinical tidbit. Okay, rotenone. We will talk about what rotenone is in just a second. Let's talk about the mechanisms and kind of how this all works. So up to this point, carbon monoxide and cyanide both act in complex 4. However, rotenone acts in complex 1. So the mechanism, this rotenone, it'll wedge itself between the iron-sulfur center in complex 1 and coenzyme Q. So here's our iron-sulfur area. Here's that coenzyme Q. This rotenone will kind of just wedge itself right here. So it's not like cyanide or carbon monoxide where it'll actually bind to the site and not allow for the electrons to bind as well. It literally just gets in the way. Electron can't get through. So the effect, NADH will stop offloading electrons. If the electrons can't continue to make their way from complex to complex, NADH can't continue to feed more electrons in. Therefore, it'll just stop. NADH will accumulate. More NAD, or rather less NAD plus is circulating. So complexes 3 and 4 will slow down pretty dramatically. So the outcome, ATP production will decrease, obviously. However, notice it's decreasing, it's not ceasing. So in this picture, we can see complex 1, 3, and 4 because these are relevant when it comes to electron transfer. However, we still have complex 2, and that's where FADH is also releasing some electrons. That means that rotenone poisoning is not necessarily acutely lethal in the same way as cyanide. Cyanide, we're stopping everything on complex 4. Nothing can continue. But in this one, we're only stopping complex 1. So we still have a little bit of input coming in from FADH. It's not quite as effective. We know that when it's FADH, we only get 6 total protons going through the pumps. So we're not getting quite as great of an ATP yield as when we're getting the 8 total protons from complex 1 through 4. But we can still survive. So most people do survive rotenone poisoning because it's not necessarily quite as bad. Now, as for what is rotenone, it's a pesticide. Rotenone is a pesticide. I read that it's also kind of a fish thing. It had a specific word for it. It's used for fish. But I want to highlight this other picture real quick. So while I was reading about rotenone, it was mentioning that when all of these NADHs are getting backed up, sometimes electrons will kind of just get loose and flow out into nowhere. So this creates these free radicals, or here we got ROS. This leads to mitochondrial damage and some other stuff that I'm not necessarily going to highlight, but the last one, neurodegeneration. One thing that I read about when I was reading about rotenone is that it's slightly associated with Parkinson's, and Parkinson's is where we get the shakes, and I know it's got some affiliation with some type of neurodegeneration. So there's some relationship here that I've never known about. So needless to say, be safe with your pesticides. Okay, and our last one is 2,4-dinitrophenol, or DNP for short. Again, we'll talk about what exactly this is in a second. Let's kind of just break down how it works. So this will break down oxidative phosphorylation by actively carrying protons across the inner mitochondrial membrane. So if we look over at this picture, we've got this DNP molecule just floating around the inner membrane space. And what it'll do is it'll actually just diffuse right on through the membrane and get into the matrix. And from here, it'll just release hydrogens, just needlessly. So DNP grabs protons in the intermembrane space, like we saw. It'll cross the inner membrane and then release them into the matrix. Well, this is a problem. We need a specific amount of hydrogens in both ways to create that gradient that allows ATP synthase to do its thing. But if we have this DNP grabbing hydrogen, crossing the membrane, and just letting them go, we effectively break the proton gradient. So the proton gradient will collapse. ATP synthase can no longer make ATP because there's no proton gradient. However, the electron transport chain doesn't stop. It'll actually just keep going. But this is weird because we're not producing ATP anymore, but energy still has to be released. So in this sense, energy is released as heat and not ATP. This can lead to things like hyperthermia and just general metabolic exhaustion. So some people in history have actually abused this thought process a little bit with weight loss. DNP used to be used as a fat burner. People took advantage of the fact that it would kind of speed up metabolism. Because ATP production slows down, metabolism is going to speed up. Yeah, you are likely going to experience some rapid fat loss. However, with this DNP, you don't have a great way to control that fat loss. And also, you can't control the metabolism. So the issue was that there was no way to control the drug. If you were to dose too high, you would just produce more and more heat. And once you got to a certain point, there was no bringing you down. And this would eventually cook you from the inside out effectively. You'd produce excessive heat and you would literally overheat to death. Crazy thing to think about. And I was reading before this that there's had been a couple, I mean, not even a couple, there was a decent amount of deaths due to DNP. It seemed to have gone a lot less popular in modern times. It seemed more popular like in the early 90s, not early 90s, early 1900s. But that's not to say that people still don't use it. I guess some people have tried to use it currently in smaller doses, and the evidence is still kind of shaky as to whether there could be some benefit to small doses of DNP, but nothing is too clear as of now. But I just thought it was interesting. DNP being used to lose weight. That was crazy. And finally, references. This first one just talks about like rotenone and the rather cyanide and carbon monoxide and kind of how all of these things affect the electron transport chain. And this other one just talks about DNP and some of the deaths associated with it and kind of the mechanism for that. Overall, I really enjoyed doing this topic. I thought this was very interesting. It was already interesting learning how electron transport chain worked in and of itself, but now learning how it can go wrong due to something else entirely was very cool. So I had a lot of fun with this. So I hope you learned something. I know I definitely did. But yeah, thank you for watching, and that's all from me.